Good morning and welcome to the Machine Learning Coffee Seminar. So today we will hear a presentation from Tomi, who comes from Curious AI, and he's going to present their new paper with the title Interactive AI and Machine Teaching of Active Sequential Learners. Please.
Thanks. So, hello. And yes, I come from Curious AI, though this work that I'm presenting is something I did while here at Aalto in the probabilistic machine learning research group. So I will be talking about interactive AI and then the machine teaching way of doing that, basically. And well, the outline, I give brief introduction to interactive AI, then talk about the machine teaching and active learners, and then how we use this as a user model for interactive systems, then some challenges and a summary. And please interrupt if you have any questions during the presentation. I think that's fine. So this is mainly based on two papers, one which was last year in NeurIPS, this machine teaching of active sequential learners, and then one workshop paper from Kai last year. And this is joint work with Mert, Petram, and Sami from this department. So, and for the purposes of this talk, AI is nice kind of shorthand for machine learning-based adaptive system. So, what do I mean by interactive AI? Well, interactive AI is actually one of FKai's research programs. I found out by looking at the website. So I took some things that relate to our work from there. So the goal is natural human AI collaboration. And the idea is that the AI can kind of understand the goals of the human users and abilities. So it needs to somehow model the human and infer beliefs and abilities from the interaction and observations. And then it should also be able to predict the consequences, like align its values with us. And well, some examples, I think recommendation systems are quite canonical example of interactive systems that are currently in use. Then there are others like interactive search or adaptive user interfaces and so on. But mostly the systems treat users as like passive data sources. They just take some, for example, clicks and use some statistical model to find some patterns in the interaction. So, and our focus is intentional human-AI collaboration in this work, so that the human knows that it's interacting with an adaptive system. So we know from research in human collaboration that theory of mind is important for the collaboration. So we can think of other people or as thinking people and attribute mental states and beliefs and intentions to others. And that's very useful for collaboration because we can anticipate what the others will do and predict their behavior, and also know that they have or trust that they have similar values to us and similar knowledge to us. So the communication between people doesn't need to be super explicit, but we can just kind of know what we are talking about from our shared background. And well, it would be nice to have something similar for human-AI collaboration. And for this, we think that both of them should model each other, or the machine should kind of model some capabilities of the human user, and also the human user should think about what the capabilities of the machine are and form kind of mental models of those. And now how to go about this? One approach is to use multi-agent modeling, which is kind of nice framework for like two or multiple AI agents to collaborate. So now the idea is that the machine can use similar models to model humans, maybe with some additional components. So one way to build this kind of multi-agent models is this machine teaching approach that we have looked into. So we will have a teacher agent and a learner agent, basically. And what is machine teaching? So it basically, the task there is to find an optimal training data set for a machine learner. So we have some teaching loss, which measures how well the learner with this given data set is able to learn some teaching goal. So the teacher knows what is the goal to teach, and now it tries to construct a data set which has a minimal teaching cost also. So it wants the learner to learn the teaching goal, but with minimal cost. And now, well, this is fundamentally interesting for machine learning. It's kind of the, it's just interesting to know what is like the minimal way of teaching some machine learning model to learn some concept or classifier, for example. And
how is the cost formalized?
Sorry?
How is the cost formalized?
Well, I guess there can be many definitions. The simplest would be, for example, the smallest number of samples that you can teach. And, well, this is
like problem specific.
Yeah. And there are theoretical work for that kind of things, like teaching dimension and such work. So there are some practical applications for this in, for example, education, which is kind of natural given the name. Then we are using it for user modeling, or at least going towards that. And then you can use it for adversarial attacks also, because the teacher can try to steer a learner towards some kind of model. So our focus is on teaching active learners. So what are active learners? I'm sure most are familiar, but in this work we assume that they kind of repeat 3 steps. So they ask some questions towards learning something, then they obtain an answer somewhere, and then they update their knowledge given that new answer. And then they repeat these. For example, we might have a logistic regression model, and there is a pool of unlabeled data that it can ask for labels one at a time. And the goal is to learn parameters of, well, the logistic regression model. So how it works is that it first chooses an unlabeled data point. For example, taking one that it's most uncertain about, or the prediction. Then it obtains the label from somewhere, and it adds that point to the dataset and relearns the parameters, and then it can loop this until it has learned enough or exhausted the data. Another example is multi-armed bandit learners. So here, instead of having a pool of data, you have some set of arms which are associated with some features, or we assume in this work. And then there's some reward distribution depending on the arm and its features. And the goal is to sequentially pull arms such that you maximize the reward that you get from pulling the arms. And now it's quite similar to the previous one. In the first step, it chooses one arm, and now it needs to balance exploitation and exploration. So because it doesn't know about the arm reward distributions, it needs to learn about those but at the same time it wants to maximize the amount of reward it's getting. And again, well, you use some strategy to choose an arm, you obtain a reward, and you add that to your dataset and relearn your model or update your model. So how we go about teaching, we think of it as this kind of a game where the learner chooses the questions and the teacher can provide the answers. So it kind of mainly modifies this second step here, that now you get the reward or the answer from the teacher. And yet the teacher has some teaching goal in mind and tries to steer the learner towards that. For example, the goal might be, well, some parameters that are known to the teacher, or just obtaining high accuracy on some test dataset. Or for the bandit model, well, it could be that you want to learn some profile of the arms, how relevant they are. This could be example of a recommender system where the arms are, for example, I don't know, movies or something, and the system tries to learn what the user wants to watch next. Right. And now the important thing in this problem is that the teacher should kind of acknowledge the sequential nature of this problem. So it can only choose the answers. It cannot choose what the learner will ask next except by choosing the answers such in a way that kind of can anticipate what the learner will ask next. And to go about formalizing this, the teacher needs to have a model of the learner to be able to anticipate it. So it needs to model the state of the knowledge of the learner and also try to anticipate what kind of questions the learner will ask. And the teaching is just answering the questions such that the learner's future knowledge will be going towards the teaching goal. So it's not trying to maximize the performance at this current question, but in the future. So, and we formalized this using Markov decision processes, or you could use model-based reinforcement learning also. And then, well, the teaching problem becomes just the problem of finding the optimal policy in this Markov decision process or planning in that process. And well, what does this mean? So we can think of, we have states like S0 is the first state, and this contains the current knowledge of the learner and also the current question. And now the teacher can choose an answer to the question. So, for example, in the logistic regression case, it could be label 1 or label 0, and then the transitions in the process happen when the learner updates its knowledge given the answer to the current question and asks another question. So it goes to some other states when it gets the answer. And then, well, this continues as far as we define some horizon or something. So, and in the end, if you define, for example, a horizon of 3 steps, you will get into some state, and you can then compare that to your teaching goal to get some, set some reward in the process. And now the task is to just solve this. Hope this was clear. So here's an example for a logistic regression learner. So this is the full pool of unlabeled data well, we can see the labels. There are crosses and circles. And given the full data, if you fit a logistic regression model here, the decision boundary will go there, the black line. And now we have the active learner. It will start with knowing 2 data points, so one from this class and one from the crosses class. And this is now without teacher, so it gets the query labels, and then it gets the label that we can see from the figure. So let's see if this works. So because it's queries data points for labels, which it is most uncertain about. When it starts with its decision boundary here, it will only actually query points from these clusters because they are the closest to the decision boundary. So it doesn't actually do very well in 10 steps. Well, this is kind of the data set is constructed to demonstrate actually this explicitly. So now, what if we have a teacher then? So it starts similarly, but then the teacher can anticipate what will happen in the future, so it actually switches some labels to make the learner query points also outside of these 2 clusters. And so now, for example, here, so then the learner is able to learn a much closer fit to the correct decision boundary. Right. So then we, towards using this as a probabilistic model, we formulated the teaching model as probabilistic by taking that the teacher's answer will be proportional to the optimal state action value of the MDP, so the Q value, which means basically if we are at this state, then we can choose to answer 1 or 0, and the idea is that after answering, for example, 0, this will be the optimal policy, or the Q function tells the value of following the optimal policy after the first action. And now we assume that the teacher will choose answers proportional to that, or exponential of that Q value. Does that make sense? Hopefully. And again, now these parameters are known to the teacher when it's teaching. And right, we can compare that to the environmental model, which doesn't. So this is like the baseline logistic regression model or baseline bandit model, which doesn't anticipate anything. It just gives you an answer based on the environmental model or the correct label distribution. Right. And now we can use this probabilistic formulation to formulate a teacher-aware learner. So now, if we think of this equation not from the teacher's point of view, but from the learner's point of view, the learner doesn't know this teaching goal. That's what it's trying to learn. But we can use this as the observation model of the learner and try to infer. The learner then uses this model to try to infer the teaching goal. That way it has a model of the teacher, and it acknowledges that the teacher is trying to teach it using some way. And now this can then be solved with inverse reinforcement learning methods. And yeah. So, and we use this kind of as a model of users or active users in interactive systems, or at least this is kind of model towards acknowledging that users are active. So the user will be the teacher, and the system is the teacher-aware learner. Yeah.
So before we proceed, I'm a bit confused about the difference between this and active learning. So in this, the difference would be that the teacher is then intentionally flipping some labels. So
Yeah.
like instead of picking a point which belongs to class X, it would mention that it belongs to class dot, and then the decision boundary changes.
Yeah.
Okay.
So the teacher is intentionally trying to, with kind of minimal number of steps, for example, trying to steer the learner towards the goal.
And if the teacher sort of already knows what the answer is,
Yeah.
in terms of like a machine learning setup, like
Yeah.
if we already know the answer, then one reason to sort of do this whole thing would be like if you have a very complicated model and then you want to simplify it, or
Well, I guess there can be multiple reasons. For example, here we use it kind of as a model that as a model of a user, which is the teacher. So now when a human user will come, we don't actually know the exact teaching goal, but we try to learn it. But well, for example, the adversarial attack is one quite clear example where the adversary might have some, like it once, for example, there's some work where you have a bandit learner and the adversary wants the bandit to pull some arm, and then, well, the adversary knows the arm, but it's still trying to steer the learner towards that. I hope that kind of answers your question. Well, we can discuss more afterwards also. Right, so going forward, what does this actually now mean that we are modeling the active user in interactive AI systems? So we assume that the user has a mental model of the system. So the user has some beliefs about the state or can anticipate how the system will adapt based on his answers. And now the model of the system that the user has is of the naive learner, like the baseline logistic regression model or baseline bandit model. And now the user can use the MDP to plan her actions based on the model of the system and tries to achieve good states in the future. And now this was the Markov decision process where the naive learner provides the transition dynamics. Well, then finally, this is nested inside the system's model of the user. So the system interprets the user's action based on this model of how the user is thinking about the system, and then tries to infer the intent or goals of the user based on that. So we might call this sophisticated learner or teacher-aware learner. And now the observation model was defined based on the state action value of the MDP. And well, of course, this is just a model of the user. The real user might hopefully do something like this, but might not do. But we learn it from the interaction. So that was basically the modeling part. Going into some results, we did some simulation experiments in Bayesian multi-armed bandit learners. So not going into too much details, we have the number of steps or number of questions on the x-axis and the cumulative reward on the y-axis. And now this is like the baseline model where you just get reward from the environmental reward model. and then you have a learner that doesn't model the teacher, and you get this kind of curve. Now, if you have a teacher which is planning using the model that I described, but not teacher-aware learner, then you get some improvement. So the teacher is able to steer the learner to accumulate more reward. Then, if you also add the teacher-aware learner, so now the learner acknowledges that the teacher is planning, then you get even better performance quite clearly. So now, so if they both are kind of modeling each other correctly. Now, one problem that might come with this is that if the learner is modeling a planning teacher, or assuming that the teacher is trying to teach intentionally, but actually if we have a naive teacher or just the environmental model, then the performance is actually much worse, because the model of the learner about the teacher doesn't match the reality. So it's interpreting the actions or the teaching wrong. But well, in the paper we actually then formulated a mixture model for the learner. So it's a mixture of the naive teacher and the planning teacher models, and then it can learn during the interaction which kind of teacher it is interacting with. So now, if we have the naive teacher and the mixture model, we get pretty much similar performance as with the matching model, and the same if we have a planning teacher and the mixture model. So that kind of guards against having wrong model of the teacher, at least in these simple cases. Yeah.
The teaching process, or do you assume some prior knowledge?
So, what was the question that? Sorry, can you repeat?
Those models for the teacher and the learner, they start appearing only during the process, or do you assume some prior knowledge?
So we assume basically that the model families are correct in this work. So we have quite strong assumptions about the models. So for example, both have, for example, the logistic regression model is known for both of them. I don't know, does that answer the question? Well, in the mixture model we have a kind of adaptive part that it can learn between two different kinds of teacher models. Okay. So, okay, we also did a very preliminary user study. This was kind of word search task. We had 10 users teaching a Bayesian bandit learner. So the task was basically that I think there were a set of 20 words, and these were the arms of the bandit. And the user was given one of the words as the target, and then the system asked questions. Is this word relevant to your target word? And the system tried to infer what the target word of the user is. And well, we used the mixture model and the naive learner as the baseline, and we saw that we get slightly better performance usually with the mixture model learner. So the system is trying to model the user as intentionally teaching it. But well, I wouldn't draw too many conclusions from this. It was quite small and simple experiment. So going forwards, while we did this work like a year ago, and when making this presentation, I kind of reflected a bit on what kind of challenges or what kind of things that we could do going forward, or maybe we should have done when we were doing this. So this is not an exhaustive list of challenges in adaptive AI systems, but just some thoughts about that. So one important thing is choosing the application carefully. So like, where do we actually want adaptive AI systems? And well, there's some ethical questions also. Many of the adaptive systems that we are using currently, we might not even know that we are using. And also, a good question is which kind of systems we can currently realize with the models we have, either computational or like theories of human behavior. In this work, we didn't really have very careful models of human behavior here. It was more like setting up the computational framework. So another problem is non-stationarity. That is a kind of fundamental problem in multi-agent learning, that if you have many agents that are all learning, their behavior is changing, then it's kind of difficult from like computational perspective, but this is also difficult for kind of user experience of adaptive systems. So if the system keeps changing too fast, for example, it will be really annoying to the user if you cannot keep up with it, or if it does like unpredictable changes. So this really highlights also the predictability of the systems, or even the statistical models that we are using, so that the user could form like a useful mental model of the system. That's kind of one assumption that we had in our modeling framework, for example. And finally, well, usually these kind of interactions or the length of interaction is quite short, and there's kind of scarcity of training data. So it's like interesting to think how we can collect more, or what kind of methods. Like, well, here we had quite strong prior models or assumptions that we know certain types of models, but you could also, or there is work like transfer and meta-learning ways of doing. And one interesting paper also studied this kind of self-play learning, which is, for example, in AlphaZero, used self-play, so the agent played against itself. But the paper that studied this in human-computer interaction learned that it doesn't really work well, at least directly, because the optimal behavior that a machine learns from self-play might not match anything what the human is expecting of the machine. So at least you might need to modify that kind of methods somewhat to get useful performance. So to summarize, I presented a probabilistic teacher-learner 2-agent model, and our motivation was to use this towards user modeling in interactive AI systems, and like having active or acknowledging that the users are active and they have mental models of the systems that they are using. And I also kind of tried to argue for using multi-agent or computational theory of mind models towards better human-AI collaboration, at least to some extent. And it's kind of clear conceptual framework, at least at high level, but I'm not sure how easy it is to actually implement for realistic tasks. So for example, the challenges that I mentioned previously, and also like computation in multi-agent models can be quite difficult, especially in nested models. Right, that's all. Thank you.
So we do still have time for questions, yeah.
Right, thanks, Tomi. that I felt was missing explicitly was the question of what the reward is, either when you define interactive AI or as a discussion point.
Yeah.
Because naively, one might say that the goal is to maximize the utility, long-term utility of the user or the learner. But that's it naive. For example, if we teach students here at Alta, the goal is not necessarily just maximize the utility of these learners, it might be maximize the utility of the society, guess, or these students all the time.
Yeah.
Engineering, for example, computer science, and they might not align. And so this question of alignment of different goals of the agent in the system is something that needs to be addressed at some point. For example, again, company-wise an interactive AI system to be used on their workforce. Now the goal of the company will probably not align with the goal of the worker.
Yeah.
And there's probably a conflict of alignment and we need to be concerned here.
Yeah, I would agree that that's important point, and well, it's not easy point either. So you somehow, for example, the complexity of the modeling in this kind of work, you can divide it into two parts, like the complexity of the task environment, where maybe the reward is defined in the task environment, and then the complexity of the behavior of the agents in that environment. And now, yeah, it's a question how you define then those goals within those frameworks. I don't know. Yeah, here we just naively used, well, logistic regression or like bandits, the default kind of default baseline ways of defining the reward.
Okay, more questions? No? Well, I could then actually ask the one that you also asked. So what do you think would be the application that would most benefit from the adaptive AI system?
Yeah, that's a good question and difficult one. So I think there are many problems where, like, we as humans and the machines have complementary skills. And currently only you kind of need to be quite expert at communicating with the machine, like programming, for example. If you want to do, I don't know, do some scientific modeling, you need to learn programming and maybe learn statistical tools and such. But there could be ways of like making that a bit easier so that you don't need to learn so much. But the system could like infer from simpler communication what you're wanting to do and try to optimize towards that. But I don't know if I have any very concrete examples.
Well, that's actually quite good for the labor problems that we have now, that we don't have the coders enough, so that would be
Right.
a good
Yeah.
application. Yeah. So are there still some other questions? Okay, so if not, so thank you again.
Thanks.